Okay, I think we already started the recording, Jack.
It started. Go ahead.
All right. Good afternoon, everyone. First of all, thank you for your time, and thank you for the opportunity to present this material related to P-HIL interfaces for grid-forming inverters. I want to touch on some topics related to some of the control, safety, and the latest cases of study for our deliverables for the UNIFI consortium. Also, thank you, Jack, for the kind introduction. My name is Javier Hernandez-Alvidrez. I'll go for Javi. And I think Jack covered most of my bio as an R&D researcher here at Sandia National Laboratories. Okay, so let me go over a very brief introduction. Let me just close this. Okay, so as a proliferation of grid-forming inverters interfacing into distribution systems and transmission system continues, I think it is important to start validating their dynamics and modeling using more elaborated test frames that will validate their behavior not only prior to commissioning these devices into the field, but also to validate them for future standard compliance, okay? The power hardware in the loop testbed provides a very flexible platform to validate such performance. And as I mentioned, not only before commissioning, but also for future standards compliance. However, the implementation of these power hardware in the loop interfaces are not as straightforward for grid forming inverters as they are for their grid following counterpart. For this reason, we have to have a dedicated configuration and validation for these grid forming devices. It is important to mention that even prior to UNIFI's inception, Sandia team has worked very actively in pioneering and proposing this type of P-HIL interfaces for grid-forming devices. So let's start with a very, very brief introduction related to real-time simulator and power hardware in the loop, or P-HIL interfaces. So advancements in parallel computing have allowed the proliferation of real-time simulators, which basically are a computational framework that incorporates hardware, firmware, and physical modeling to operate in a parallel fashion. And this way, we can facilitate real-time simulations with small time steps. The figure in this slide shows the basic architecture of a real-time simulator, on which basically we have a bank of CPUs, or normally we call them cores, and those are basically the devices that host our simulations or simulation models. But also we have to interact, if we want to make it a power hardware in the loop, we have to interact with external power electronic devices. And normally we use, or what most of the vendors use, an FPGA due to its embedded system capabilities to interface with such devices via analog input and outputs. And there is always a communication or a fast communication in between those CPU units and the FPGA. So in a nutshell, it's this type of computational resources are a fine tribute to the usage of parallel computing. Now, what is a power hardware in the loop interface? Briefly defined, it's that simulation scheme that incorporates actual real power electronics assets into a real-time simulation, okay? Under these type of simulations, we can test inverters or power converters under different grid conditions that can be difficult to implement or replicate in the field or with pure hardware, okay? The grid following inverter control structures are relatively easy to interface on their P-HIL scenarios. Actually, the figure here shows one of these cases on which we have a simulated system where we can simulate different grid conditions. And then we have to identify a bus or a node where we want our device under test to interact. And once we identify the node, we sense the voltages at that node, and we use those voltages to drive a grid emulator. And we provide those voltages or those outputs of this grid emulator to the interconnection interface for a device under test. And once we interconnect, we could sense the current at hardware level, and we close the loop by feeding that current into our interconnection bus at the simulation site. Now, having said this, if this device under test is grid following in nature, then the interconnection or the initial interconnection is pretty much straightforward because of its inherent synchronization capabilities. It will detect the voltage and will synchronize and it will perform the interconnection. However, if, or this is an issue that we had back in 2019 when we start developing some of the interfaces, if this device regulates its own voltages, like the grid forming device, and the power amplifier also is driven by the voltage at the simulation level, we have to achieve synchronization prior to the initial interconnection. Failure to do so could lead to unstable behavior or even damage on the integrity of the grid forming device or even the power amplifier. And for this reason, we have to propose different schemes for P-HIL interface, particularly customized or tailored for grid forming devices. And the first basic P-HIL interface that we proposed back in end of 2018 was as follows. So as I mentioned on the previous slide, it is not recommended to make a bare connection between the grid forming device and the grid emulator. And for this reason, we propose to use an interfacing reactor in between the two devices, okay? And we also have to take into account not only the value of the inductor, but also the parasitic series resistance. So if we want to have a good accurate result between the hardware and the simulation results. The underlying principle under this P-HIL interface is that we sense the voltage on the grid forming terminals, and then we feed those sense signals into a voltage controlled voltage source at the simulation level. That way we can guarantee that the voltage at bus 1, either in simulation and at hardware level, is the same. Also, we replicate the interfacing inductor. And here, I want to highlight some important things about this interfacing inductor. Make sure that you take a good and accurate measurement of the hardware devices so you can replicate it accurately on the simulation. Also, and I will explain later, there will be cases where this electrical network power demands will be higher than the power rated of the rated power of our device here. So we have to scale these properly so we can accommodate the maximum amount of power this delivers to deliver the maximum amount of power of the electrical network. I will delve more into the details on the next slides. But the main principle of operation is a partial circuit duplication scheme where these two equalities should hold. If they hold, we can simulate an electrical network, and any changes in the dynamic, in the dynamics of the electrical network or the simulated electrical network will be reflected in amplitude and phase variations on node number 2 at simulation. But since these changes are also replicated on the grid forming, it will translate those on the grid emulator. Those changes will be replicated also on node 2 at hardware level. And if these two interfacing inductors are close, or the values are very well measured and then replicated at simulation, then we will have similar conditions in hardware and software. In the case where we scale it by a factor K, then those conditions will be amplified on the simulation level. Or basically, the way I describe it is that we operate the Ametic or our grid emulator as an electronic load. that follows any electrical changes in the simulated network. Now, how does it look like in real life, or what are the actual elements that we have right now, or we currently have at Sandia? So this is a diagram that describes most of, or basically describe all the elements involved in this P-HIL interface. And those are the actual hardware devices that we use. So you could see that we have a battery emulator to drive the DC side of any of the two available grid forming units that we have right now. The one that we are currently using is the Westec, but we have the capability to interchange it for the ABB, and we do this manually, and it's a process that could take us no more than 15 minutes. We also have to build our own inductor bank. We also have the grid forming, the grid emulators in parallel. And the current vendor that we use for a real-time simulator is the Opal RT. Last but not least is this contactor that we have in between the two devices. I didn't put that one in the previous diagram, but as a safety note, guys, always protect your equipment and always use a contactor. If you have the possibility to use it, all right? And I will delve into some of the details on how to use it later on. I don't want to spend so much time on this one, but we have proposed other power hardware in the loop interfaces that are more elaborated, that require more control schemes. Basically, it's the same principle on which we sense the voltage on the grid forming device, and then we send them to the simulation to drive a voltage control voltage source. And in this case, we could use only, just to validate it, we use P and Q loads on the simulation side, but this could be replaced by more elaborated simulation systems. From the control perspective for this particular P-HIL interfaces, we want that the current at the simulation, at the hardware side, tracks the current at the simulation side. So this becomes a control problem. And to accomplish this, we create our own control scheme on which we manipulate the variables on the power amplifier, which basically changes the amplitude and the phase angle, so we can track or have a good track of the hardware current on the simulation currents, all right? In order to accomplish the control scheme, we use a synchronous reference frame PLL and a PI controllers to perform the control actions, all right? We have tested these P-HIL interface with a good degree of accuracy and with a good degree of stability, but we have used only residential grid forming inverter, the Outback. And we still are pending to try this methodology with 100 kVA, with one of our 100 kVA inverters. Also, one of the drawbacks on this one is that it is always difficult to tune these controllers, but we are, it's a work in progress to propose a tuning procedure based on step responses from experimental data. We also try some frequency sweeps in there, but to try to characterize with butter plots, but you could see that since those type of tests should be in small signal, this type of noise, as you see here, obscure some of the dynamics. But I think we're still in good shape to do some step responses and try to come up with a procedure to tune up properly or optimize the tuning of these controllers. We also have some emulation results on tuning these controllers using model predictive controls. But I think this is a work in progress, and we will continue and probably report this on a paper on the next year. So I'm going to show some of our latest results using a 100 kVA inverter, using the very first proposed method of interfacing. But those tests were performed during calendar year 2024. And they were in compliance with some of the deliverables that we have for the UNIFI consortium, particularly the one related to demonstrate a stable P-HIL evaluation of a 100 kVA commercial unit operating from black start scenarios on the simulation side, and also use a representative simulation system. The device of the test, well, here are some of the descriptions of a description of the main features of the device under test. Is the Westec unit. Is manufactured in Germany. It's a 3-phase grid-forming inverter. It is rated 100 kVA at 480 volts. It is highly programmable via Modbus, and it is very useful because it has a lot of protection capabilities in terms of frequency and voltage, and it also comes with a programmable frequency and voltage droop characteristics. It is not as fancy as the ABB, on which it has a really good screen for user interfacing. For this one, we have to develop our own scripts to program some of the registers needed for commissioning. Also comes with a line frequency isolation transformer internal, which is a great addition. I gotta say that commissioning was complicated. It made it all the way from Germany with some loose components, with some other parts were also broken. Some of them require replacing, some others requires just tightening certain screws. But one of the nice things about the customer service is that they provide the schematics. So with the schematic in hand, we have to go over almost the entire system. And it gives you a good overall understanding of how the system it's assembled. So far, we are very happy on how this inverter has responded to power hardware in the loop interfaces. Now, regarding safety, I would like to make a quick pause here and just give some of the safety practices and recommendations from our side. The first one, if you have the time, try to emulate your entire system or put your entire system on an offline simulation. And I know we may not have, I don't think we will have an accurate model of the inverter, but at least try to model the basic characteristics of droop, all right? Same goes for the power amplifier. And run those simulations offline. If they are unstable, our advice, because of our experiences, is just don't run the P-HIL experiment until you have a good emulated system that it's stable. As I mentioned before, the contactor is your friend, and use it. Please use it as a front-end protection device. Now, how to control the contactor? Well, it's up to you guys. But in our case, and since we have significant amount of computational power provided by the Opal RT machine, we use it to create our own protection schemes. And we go for the basics: overcurrent, under voltages, but you have the opportunity to be creative on how you protect your device here. If you don't have enough computational power, or you have all the cores allocated for more elaborated simulated systems, well, I've seen people using SEL devices. Just an overcurrent device will do the work. Just make sure that this contactor is your first layer of protection. And if this is going to be your very first P-HIL test with that particular unit, program the contactor to just operate for a short period of time, and then analyze the transient response. I will show some of the testing that we do here at Sandia, and our first initial test is for synchronization, and we try to do it for 1 second. All right, and then we just disconnect the contactor, and we just check that the transient right at the interconnection, and we just check that we don't see any unstable behavior, and that give us or set the foundations for more for longer tests. Okay, but I think that this type of testing has saved us for really damaging the equipment, because we disconnect after 1 second we make the first interconnection. And also, check your voltage sensors for DC offset voltages, and try to compensate for that, or calibrate your sensors regularly, guys. I'm going to show a case where we had DC offset presence. We didn't realize it, and it was because we keep a short period of time the contactor on is because we didn't really let the unstable behavior to damage any of the devices, okay? But we also have learned the hard way, and we have damaged some of the, at least the over voltage protection boards from some of the inverters. Be mindful, guys. It's our advice, and these are our 2 cents regarding safety practices and recommendations from our experience. As a second layer, and if you have the opportunity, read, as a second layer of protection, read your manual and identify any frequency or voltage protection parameters. We did that for our Westec unit, and we identified and created these, I would say, right-through procedures, but identify the main parameters for protection. So you could set switch on voltage and frequency conditions as are highlighted here on the green areas. And if possible, try to design your own right-through procedures, okay? And verify them, validate them. So you are certain that you have your equipment very well protected against instability or overcurrent or under voltage scenarios that we really don't want during stable conditions. So the first step and the approach towards most of our deliverables here at Sandia is that, okay, we read our main goal is the deliverable to UNIFI, but we divide the task over subtask. Each one will be incrementally more complex than the other, on which we start with the basics. We start with synchronization, and we start with safety, and we start the initial interconnection. And then we start taking it to more elaborated, simulated scenarios. So for our first P-HIL interface, it was just to validate safety, long-term stability, but also synchronization and the initial transient on the initial interconnection, okay? So the underlying principles for this very first test or for this very P-HIL interface are, again, we sense the voltages on the terminals of the inverter. Notice the use of that bandpass filter. It come up handy later on. For this one, we changed the scheme a little bit. So we just want to focus on synchronization. So we sense the 3-phase voltages, and then we use those voltages to tune a synchronous reference frame phase lock loop to obtain the phase angle of the inverter. And we have the capability to provide phase list compensation by the user on these inputs right here, okay? Just in case that we have to compensate for the delays introduced by this bandpass filter. Also, this input here that is also user programmable, we use it to allow the inverter, once we interconnect, we'll use it to allow the inverter to provide some real power into the real and into the grid emulator. Okay, and for our first test, we wanted, oh, I forgot something else. We decompose into DQ, and then we use them again to reconstruct the voltage signals that will drive the power amplifier or the AMETEC. But this time, the frequency of the signals, we know they will be in sync with the signals of the grid forming device. And then we're ready to close the contactor, all right? So the first test here is, as I mentioned before, and I sound redundant, is to validate synchronization and close the contactor to analyze the transient behavior. And second, if we have a stable dynamics, then we start ramping up the value of these input, and we start ramping up the angle. That way, this grid forming device starts to inject power into the grid emulator. So we went ahead and run the test. Obviously, we have this contactor here that's the one that command the closing of the closed loop at hardware level. So we gave it a try, and for this particular test, the signals driving the AMETEC achieved synchronization with the sense voltages, but initially we didn't have this bandpass filter here. All right. And once we close the contactor, the inverter seems to start working fine, start ramping up the current. I'm showing only current on phase C, but the behavior was basically very similar to on the other phases. And then it stopped providing current, and then the voltages start to go and do these weird transients and then collapse. And as you could see, what helped us out here is that we programmed the contactor to last only 1.6 seconds. And that may be even too much. So my advice would be 1 second. But you could see how the inverter tried to interconnect several times until it completely tripped off. We didn't damage the device, but at the same time, we have to scratch our heads for, I would say, 2 weeks, trying to figure out what was causing this sort of instability. And it was that we have DC offset issues caused by one of the voltage sensors that provide the voltage measurements at the inverter terminals. And that was the problem. So at that time, we didn't have a new sensor. So we gave it a try by introducing this bandpass filter in between the sensor and the synchronous reference frame. And this was implemented at software level or in the simulation. And once we put that bandpass filter, we have a really clean and nice interconnection, and the simulation went on ramping up the current, ramping up the power delivered by the inverter, as you could see here. And you could also see a zoom version of the currents, but we still program the contactor to close and open after, I think on this one was after 2 seconds, okay? But you could see how it is nicely start ramping up the current. The same dynamics were for currents A and B. But yeah, this is the type of test that sets the foundations for more elaborated test. But we also wanted to give it a try. So instead of using a gradually ramping behavior on this input, we wanted to see how the inverter reacts to a step load on this phase angle right here. And that will actually resemble a black start scenario. And once we did that, we will be more confident to move forward with more elaborated testing or P-HIL scenarios. So here we evaluated, as I mentioned, the load step in this parameter here, and notice the long-term stability, but also notice that the program droop is being activated on the grid forming device as we demand more power from the inverter into the grid emulator. So this actually resembles a black start scenario, and it will give us the confidence that instead of having a PLL, we can have an actual circuit that can operate during a black start scenario, okay? So the second P-HIL interface, we relied on the fact that we have a secure system in terms of ramping and step load responses, but we wanted now to incorporate the actual partial circuit duplication scheme on which that allowed us to have a more elaborated electrical network on this side. Notice also that we have to use a lead compensator to compensate for any delay introduced by the bandpass filter instead of using the PLL. But still, once we are on steady state behavior, we drive the signals of the AMETEC and synchronizing, and it will allow us to run a step load on this electrical network that resembles a black start scenario. Again, this partial circuit duplication scheme allows for the real and reactive powers on the simulated and hardware side to be dictated by these two equations, on which we not only take into account the external reactor, but also their corresponding series resistances. And again, I think this is a very, very important aspect of this type of P-HIL configuration. As I mentioned before, there will be cases where our simulations real and reactive power will be a K factor higher than our hardware real and reactive power, or our hardware limitations by the ratings of the grid forming inverter. When that is the case, we use this K factor to properly scale down the reactors at simulation level. And failure to do this scaling or properly scale factor will make the AMETEC to drive more current out of the inverter or exceed the rating current, and will definitely trip our protection scheme. So we have a paper in which we describe the procedure of this scaling factor, and we recommend it to follow in case that this electrical network demands more power than the rated power of our device under test. But we still can provide, we can do a simulation if we do the proper scaling, guys. And I like to emphasize on those scaling factors. Okay. So for this particular test, we use on the electrical network side a balanced resistive step load of 20 kilowatts, all right? So on this one, we didn't scale because this inverter is 100 kilowatts. So we just wanted to test how they will respond. And we also wanted to test the level of accuracy between the simulated signals and the hardware signals, okay? And also help us to validate the simulation strengths and dynamics against the hardware side. The first results that we run on this one were unsatisfactory because at hardware at simulation, we have a mismatch on power and current of 35%, okay? And again, we feel a little bit disappointed about this test because we tried to figure out, because we struggled to figure out where the source of the inaccuracies were. So eventually we realized that we didn't take into account the isolation transformer or the reactance of the isolation transformer of internal to this device. So we went ahead, we opened up the inverter, and we measure 0.3 millihenries. And we add them up to the 1 millihenries of each one of the phases. And once we did that, we just incorporated that into our simulation, or we changed the values in our simulation or updated those reactor values in our simulation site. And then we achieve at least good accuracy during the steady state behavior, right? So we show, it definitely show significant improvements on the steady state accuracy. Then we decided to compare the hardware and simulation with a test with pure hardware. So we have a load bank here at Sandia, and we just provided the step load of 20 kilowatts. And you could see that we achieve a good level of accuracy between the pure hardware test and the simulation of our P-HIL interface. However, we still have mismatches on the initial transient on the hardware level. And that this one is also translated into the currents at hardware level. And we're still trying to figure out what the source of those inaccuracies at the initial transit, but at least we accomplished really good level of accuracy on steady state behavior. Here I think we believe that it is the fact that we are emulating a load instead of using an actual load, all right, an actual discrete load. And I think this is the price that we're paying for emulating a load instead of using an actual load, right? Let me see if I cover all of this figure. Yeah. So those two results were some sort of the deliverable for last year on UNIFI. And also over last year, we start to prepare for our deliverable for this year, which will be, strictly speaking, will be a test on which we will put a power hardware in the loop on the simulation side that will experience, and then we will put a second source of generating, a second generating source. And instead of being a generating source, the strict definition will be loss of the last synchronous generator source. But first, we wanted to know how the inverter under this P-HIL environment will react under a second generating source that is a hybrid of a grid forming device or a grid forming average model with surge droop control, And we also wanted to evaluate the initial interconnection of this second source using a PLL just for the interconnection purposes, okay? And we agreed that will be a synchronization issue. That's why we include the PLL. And once we achieve the initial interconnection, we switch towards the search Druck control. But yeah, again, attempting to just interconnect, even if it is at simulation level, this second generating source to share a load, and we don't have any synchronization between the source and the voltage at the point of common coupling, definitely is going to drive the system towards current spikes that may drive the simulation unstable. We run a simulation offline, or basically on our emulation, and we did it without synchronizing. And without synchronizing, you see these current spikes. So that gave us the hint of do not perform this without a synchronization device. So that's why we included this PLL here. But those current spikes were given by the emulation. So this one helped us to highlight the importance of emulating your system with an offline simulation of your entire system. It's strongly recommended, guys, to see this type of behaviors, okay? So I think this one covers that part. And then we went ahead and implemented this PLL, and then we implemented the actual P-HIL experiment, okay? And let's try to follow the chronology of the events. So at T1, and yeah, so the two plots here, the one on the top describes some of the dynamics in terms of real power of the grid forming device at hardware and simulation, the device we're testing. And I wanted to monitor the currents of this second generating source and just check its dynamics, okay? So at T1, the hardware contactor is closed and the simulated load is still disconnected, all right? And the device under test in hardware and simulation powers are nearly zero. Then at T2 or second 51, we engage this load with the second generating source still disconnected. So you could see that the grid forming device takes the or supplies the load entirely, all right? And then you use this time to synchronize the PLL of the second generated source at simulation and get it ready for closing this contactor. And we close this contactor number 2, or well, at T3, I don't want to confuse you. At T3, we close or we interconnect this second generating source once it has been in sync with the node or which we want to interconnect. And you could see that now the grid forming inverter starts to drop its power supply to this three-phase load. But also notice how the current on this second generating source starts to increase. But also it is important to point out or to notice that we don't have large spikes. So this one, again, highlights the importance of synchronization prior to the initial interconnection of this second generating source. And then we went at T4, we went to the actual test that of disconnecting or loss of the last generating source and realize if the grid forming inverter provides the voltages during this, I would say, islanding scenario. So we disconnect the source at T4, you see that the current immediately drops from the second generating source, and you see how the grid forming inverter immediately forms the island and starts to supply the load entirely again, okay? So this one set the basis or the foundation for a second generating source that it will be more elaborated in nature. We actually are working on the design of a model that includes diesel genset, and we're trying to use some of the parameters of the actual 250 kVA diesel genset that we have here at our facilities at Sandia. But the main deliverable this year from Sandia to UNIFI will be a similar test like this one. But instead of using this type of hybrid source, we are going to use an actual model of a diesel genset. And but we needed to run this test again for safety purposes, and also as a stepping stone towards a more elaborated model of this second generation source, which again is going to be a diesel genset model. I think this is just yes, more elaborated analysis of the previous test of the loss to the last generating source. Again, we see this power retention shoulder on the hardware side. And again, we still haven't figured out the exact root of it. We have some hints of it. It may be an issue with the inverter that seems to curtail the current during this shoulder retention period. But we still need to figure out exactly what is it, or if this current curtailment is related to this power curtailment. But again, notice the absence of high current spikes at the moment we interconnect the second source. So again, highlighting the importance of synchronization. Right. So again, all these tests, it set us the foundation for a more elaborated power source on the or to replace this hybrid source with the diesel genset. And our last deliverable for last year is to provide a P-HIL interface experiment with a more representative distribution system. And for this one, we picked this model of a distribution system called the Old Forge National Grid model. It is a 150 node distribution system. It's fairly balanced, where the loads add up to 8 megawatts of real power and 1 megabar of reactive power. Definitely for this type of P-HIL scenarios, we needed to scale the P-HIL interface inductor on the simulation side to handle the load capacity. Okay. I think here I'm just, oh yeah, this type of model is fairly more complicated. So we have to use different cores. For those familiarized with OpenRT, we have to use different subsystems to simulate the distribution system model. Yeah. Yeah, basically here I'm just describing that we have to divide in different subsystems and assign it to different cores. The interface that we currently have for that one, notice that we have a lot of monitoring of the signals. We have full control of the enabling and disabling of the contactors of the simulation models. We have a dedicated section merely for protection, guys. So it's highly advisable that you have a console where you have the capacity to react fast in terms that in case that the system goes unstable. So yeah, allows visualization of the control in critical variables. Also facilitates the calibration procedures for all of DC compensation issues that we face here with some of our sensors, phase lead compensation, and the proper scaling of analog and input signals using between the hardware and simulation devices. All right. So for the national grid and the deliverable for this last year was just to achieve long-term stability, but also check that the inverter adapts to the proper scaling of the interfacing reactors. And again, the test consisted only of running or activating the contactor for a short period of time, right? And we leave normal, and then after we activate a contactor with zero power interchange between the two devices, then we engage the national grid model as a matter of a black start scenario. And we recorded some of the signals, and we have a very, very successful and stable test for this particular stability assessment. But you could see that we run the test for almost 10 seconds. I think I mentioned on the previous slide that we run it for 1 second. So this test of 10 seconds for a stable behavior, we run it this last, I think, a couple of weeks ago. So we were able to achieve a longer stability. And not only on, and we just recorded any real and reactive powers on the hardware side, and also the currents on the hardware side. You see that we have some sort of level of imbalance, and the inverter is able to take this imbalance on the phases, and this type of testing resembles a black start scenario, but that was not well, it was part of the deliverables, but at this point, we just wanted to assess the long-term stability of the entire system. And this test give us the confidence that we can, that the system is stable, that the P-HIL is stable, and that it will allow us to go for more elaborated testing scenarios, all right, on the simulation side. We will try I-landing again. We will try loss of the last synchronous generation test on this national grid model. And I think that one will wrap up our deliverables for this year on the UNIFI regards. Some of the conclusions that I want that we draw about this on these results is that, well, first I like to highlight the importance of safety, guys. Normally our deliverables don't focus on safety. They take it for granted. But if there are research institutions or that try to accomplish this type of P-HIL scenarios, don't hesitate to contact us. We could share experiences. We can probably give you some advice in terms of how to make your P-HIL experiments successful, particularly if they are for grid forming units. All right, so don't take for granted that you will use the same interfaces as you use with grid following devices. And basically, I wanted to show some of the results that we had over the last calendar year regarding black start scenarios, regarding stability, regarding synchronization, and regarding the testing of a more representative system like the national grid that will allow us to go for more elaborated tests, or change the conditions on this grid simulations on the simulation side of the P-HIL setups. So I think that one wraps up my presentation, guys. You have any questions, by all means, I can stay longer if you guys want. But thank you so much. I really appreciated your time, and I'll keep you posted with more results. And definitely looking forward for more presentations like this to present all of the work here at Sandia. Thank you very much.